Hello and welcome to The Daily Space. I'm your host, Dr. Pamela Gay.
And I am your host, Beth Johnson.
And we are here to put science in your brain. There is a lot going on in astronomy right now, and this is a shortened week for us with Veterans Day. This means today is going to be rapid fire science, and we're already planning out the rest of the week. Specifically, we're going to focus the first half of Friday's episode on the newly published Decadal Survey, a document that sets the priorities for the next 10 years of astronomy.
But before we can do that, we have news. So much news. And an interview with Dr. Rosanne Di Stefano from the Center for Astrophysics, Harvard and Smithsonian regarding the recent announcement of the possible first detection of an extragalactic planet.
And now to get to that news, and it is good news. Over the weekend, mission operators were able to return the Hubble's advanced camera for surveys to science operations. Additional instruments remain in safe mode, but this is a promising start. After 31 years in space, Hubble is starting to feel like the character in a science fiction movie who has to keep working far beyond a reasonable age for the benefit of everyone around us. Slated to be turned off more than a decade ago, the mission has hit the point of just being tired, and glitches in the hardware have been catching our attention more and more often. Hubble is uniquely able to study the sky in wavelengths spanning from ultraviolet to infrared, and this gives it something of a human view on the sky. While many folks often refer to JWST as the successor to Hubble, the reality is JWST will see the sky in longer infrared colors. At this time, no true replacement to Hubble is planned, and the entire science community is trying to get as much data out of this telescope as they can before it finally ceases to function.
Some of Hubble's most amazing imagery has documented the formation and evolution of stars, and some of astronomers' most awkward naming has been applied to this amazing science. Invisible light, like we see with our eyes, cold, dark clouds of gas block not only the light of the stars behind them, but also the light of the stars forming inside them. As the observed color changes and these clouds are observed in redder and redder colors, we are able to see more details. In a new image of a region of the Coalsack Nebula in Cygnus, Hubble reveals both two newly formed massive stars and also two smudges of star formation. And here is where the naming of things goes oh so very wrong. These two clouds are named free floating evaporating gaseous globules, or FREGs. And these FREGs are good FREGs, and they are forming stars. Over time, the ultraviolet light of those new stars will blast away the gaseous globules, allowing these stars to hatch from their FREGs. This is one of the most ridiculous acronyms we've seen in a while, and it is the latest recipient of our Babies Award. That's a bad acronym or backronyms in everyday science. Kudos to everyone involved in that acronym. You created something thoroughly punny.
And now for something entirely different. Tomorrow's Rocket Roundup is so jam-packed with launches that we're letting human spaceflight news sneak in with our science. Late on Monday night, November 8th, Eastern Time, Crew Dragon C206 successfully completed its second trip to space with a splashdown off the coast of Pensacola, Florida, bringing back the members of SpaceX Crew 2 mission, NASA astronauts Shane Kimbrough and Megan MacArthur, ESA astronaut Thomas Pesquet, and JAXA astronaut Aki Hoshida came back to Earth after 199 days in space. They suited up and undocked from the space station in the afternoon before landing in the evening. After undocking, Crew Dragon Endeavour performed an autonomous flyby of the International Space Station to allow the astronauts to photograph it to analyze its condition, the first time this was done since 2018. Astronaut Pesky took pictures out of the small window in the forward hatch of the Dragon to accomplish this task. Commander Kimbrough and pilot MacArthur were ready to take control if they needed to, but Dragon did all the maneuvers by itself. After a full orbit of the station, Dragon performed 2 more burns to depart the ISS. Also returning with the crew is 240 kilograms of science results and old hardware from the station. These supplies were secured to the floor of the capsule. Crew 2 was originally supposed to depart after Crew 3 arrived, performing a direct handover, but instead they returned before the launch of Crew 3. Crew 3 has been repeatedly delayed due to crew illness and poor launch weather. The Crew Dragon is only rated for 210 days in space, so delaying the departure for a direct handover would have pushed the capsule past the limit unnecessarily. In addition, the landing weather was forecast to get worse every day they delayed returning, so the 8th was the best day to meet all of the requirements. The crew of Soyuz MS-19 are still on the station, keeping it operating until Crew 3 brings it back up to its full complement of 7 astronauts sometime later this week. After the break, we'll be back to talk about new Earth images and volcanic eruptions.
On September 27th, the Landsat 9 orbiter launched, and a little over a month later, it is returning awesome images that will in time turn into amazing science. The mission had first light on October 31st and celebrated Halloween by looking at how Earth was dressed up for the season. NASA Administrator Bill Nelson says it best. Landsat 9's first images capture critical observations about our changing planet and will advance this joint mission of NASA and the U.S. Geological Survey that provides critical data about Earth's landscapes and coastlines seen from space. This program has the proven power to not only improve lives, but also save lives. NASA will continue to work with USGS to strengthen and improve accessibility to Landsat data so decision makers in America and around the world better understand the devastation of the climate crisis, manage agricultural practices, preserve precious resources, and respond more effectively to natural disasters. The first set of images include Detroit and neighboring Lake St. Clair, the Florida coastline, Navajo County in Arizona, the Himalayas, and the coastal islands of northern Australia. And while Landsat images are always amazing and provide a wealth of scientific information, this newest member of the Landsat family is poised to help us understand how the growing issue of climate change is affecting regions all over the Earth. That's because of improved instrumentation over the previous satellites, Landsat 8, which is still in orbit, and Landsat 7, which is the satellite being replaced. One major difference between Landsat 7 and 9 is the enhanced color differentiation. Where 7 could only detect 256 different shades of a color, Landsat 9 can detect over 16,000 shades, which means this latest satellite can detect much more subtle changes than ever before, especially when it comes to darker regions such as forests or water. All this information could help us get a handle on water usage and wildfire impacts, as well as the effects of climate change on coral reefs, glaciers, and ice shelves. Karen Saint-Germain from NASA explains, in a changing climate, continuous and free access to Landsat data and the other data in NASA's Earth observing fleet helps data users, including city planners, farmers, and scientists, plan for the future. NASA's Landsat 9 team will now conduct a 100-day checkout period, which will test and calibrate various instruments and systems on the satellite before the mission is handed over to the USGS in January 2022. Once the satellite is fully operational, it is expected to collect about 1,500 images of our planet every single day, with a full picture collected once every 8 days. All of that data will be freely available to the public from the USGS website. And we suspect we will be bringing you even more climate change stories next year once scientists start analyzing the information.
This next story feels like an amalgamation of so many stories we've covered before. Satellite images, check. Tree cores, check. Volcanoes, check. And all of it adds up to a newly rediscovered bit of information first published in 1975. Something in the soil of a soon-to-erupt volcano can make trees in the region greener than usual. New research published in the journal Ecohydrology takes a look at how a narrow band of trees, 30 meters wide by 2 kilometers long, on Mount Etna in Italy, turned greener in 2001 just before an eruption in 2002 along the same stripe. The trees, of course, were destroyed in the eruption, and the difference in greenery was really only noticeable in satellite images. This led researchers to look at some historical observations, including a similar phenomenon that occurred at Mount Etna back in 1973. Additionally, further evidence from the phenomenon was found in images of Mount Ngiragongo, Democratic Republic of the Congo, in 2001, as well, which was also followed by an eruption. Of course, satellite imagery isn't enough to understand what is going on, so the team collected some tree cores with the help of the Swiss National Science Foundation. Since the trees along the eruption zone were destroyed, they focused on trees within about 150 meters of the 2002 eruption at Mount Etna. After an analysis of the carbon isotopes, the results showed that the tree rings were similar during a control period as well as the eruptive period. So the greening effect was not the result of carbon dioxide. However, another isotope, oxygen 18, was shown to drop during the eruption season, and that could mean that the enhanced trees, well, they received more water vapor from the volcanic steam in the soil. Now, this doesn't mean that we should hunt satellite images for lines of enhanced trees, although perhaps the new Landsat 9 will be able to do just that. But this is another tool in the box for predicting where a volcanic eruption will occur. We love multidisciplinary science, and this team involved experts in forestry, soil science, volcanology, biochemistry, and ecology, plus satellite imagery, field work, and lab work. We hope to see more from this group, and we'll bring it to you here on the Daily Space. After the break, we'll be back to interview Dr. Rosanne Di Stefano about the recent discovery of what could be the first planet in another galaxy. Stay tuned.
Welcome back. Joining me now is Dr. Rosanne Di Stefano from the Center for Astrophysics, Harvard and Smithsonian. Dr. Di Stefano is the lead author on a new paper in Nature Astronomy that lays out evidence for the discovery of possibly the first planet found outside the Milky Way. Using a modified version of the transit method that scientists use to find extrasolar planets, Di Stefano and her team observed an X-ray binary in the Whirlpool Galaxy and found a dip in the X-ray signal that could indicate the presence of a planet. Thank you for joining us, and welcome, Dr. Di Stefano.
Thank you.
So, how did this particular research come about? What led up to it?
Well, it was actually an interesting case because we had not spent years thinking about planets, planet discovery in other galaxies, but we had made a kind of an observation. This was back in 2018. It was a theoretical observation when Nia Amara and myself realized that the X-ray emitting region in most X-ray binaries is rather small. In fact, comparable in size to planetary dimensions. And so this has the consequence that if a planet passes in front of such an X-ray emitting region, then it can totally cover it or substantially cover it and produce a detectable dip or transit.
And in the case of this particular X-ray binary, which is M51ULS1, how did you find that particular one?
Well, we had to cast a wide net because we really had no idea. And we're only, with this example, we're just starting on a long road to find out what fraction of X-ray binaries have planets. So we started with all of the X-ray binaries in 3 galaxies. Chandra and XMM both observed some of the larger, nearer galaxies fairly frequently. And so there was, at least from Chandra, about 10 days worth of data on these 3 galaxies, on each of them. That doesn't mean that they looked for 10 days continuously. It means that over 20 years, at various times, the galaxies were looked at, and that if you put it all together, it comes out to about 10 days. And so we had a colleague, Dr. Ryan Urquhart, who had just studied the data from these three galaxies. He was looking at all of the X-ray sources, and he had compiled the data in such a way that it was easy to collect what we call the light curves. That is the record of the intensity or count rate versus the time. So we just took everything in all three galaxies. That was several hundred separate X-ray sources and about 2,600 light curves, because many of the sources had been observed multiple times. And so we just studied all of them. And we developed a condition that we thought, a set of criteria that we thought would help to identify planets. And that set of criteria gave us one result. And that was one of the light curves of M51 ULS1.
So, will you explain for our audience what an X-ray binary is and how you're detecting this?
Right. An X-ray binary is a very interesting thing. What you have is you have a compact object, a stellar remnant, white dwarf, neutron star, black hole. In the case of a galaxy like this, we really generally see the ones that have a neutron star or a black hole with a companion that is having matter stripped from it, and the matter then travels toward and accelerates toward the compact object, picking up energy and eventually emitting an X-ray wavelengths. So the X-ray emission comes from the matter that is accreting onto or in the region of the compact object. And that's what we mean by an X-ray binary, basically. So they're interesting systems because whereas in a galaxy like M51, you might have hundreds of billions of stars, there may only be at any one time about a few dozen or several dozen active bright X-ray sources. So we can actually look at most of them in a field of view of the Chandra Observatory or with XMM Newton.
And because they're so few and they're fairly small, they're easy to differentiate from another and from the rest of the, say, stars in that galaxy.
Right. In other words, you can easily see, there's one here and there's one here and there's one there. They're very resolvable in contrast to those hundreds of billions of stars. I like to think about them as the Galileos or the Einsteins or the Shakespeares of their galaxy, right? There are lots and lots of stars, but only a handful of these very bright X-ray binaries.
All right. Well, I want to talk to you a little bit more about how you narrowed it down to being possibly a planet, but we're going to take one quick commercial break and then we'll come back and talk about this some more. All right, welcome back. With me again is Dr. Rosanne Di Stefano, and we're talking about a possible extragalactic planetary detection in the Whirlpool Galaxy. So, Dr. Di Stefano, how did you narrow this down to being a potential planet? I saw in the press release that they listed several different things that it could have been. We always say that when it's something unusual, it's probably gas and dust, but you ruled that out. So
right.
How did you rule out various things?
Well, the gas and dust is an excellent example because X-ray binaries have amazing flows of plasma, going in toward these compact objects. So a lot of that is in the form of an accretion disk, but there also can be clouds of gas and dust or irregularities in the disk. And the matter in these clouds is a little more diffuse in contrast to, let's say, a star or planet that has a fairly well-defined surface. Now, they may have an atmosphere, but that atmosphere is thin. Whereas if you have a gas cloud, it has a fairly significant diffuse component. So when a gas cloud passes in front of the X-ray source, you begin to see signs in the X-rays that the X-rays are interacting with matter. and the spectrum of the X-rays that we receive is changing. And so that's a signal that's very useful for scientists, actually, because it gives us a diagnosis of what kind of material is there in the environment of the X-ray source. And then when you look at the shape of the dip, because these can be kind of irregular, these clouds, you get a kind of a shape that can be a little bit ragged, or it may differ from time to time if you see one dip versus another. Our dip was a regular shape, which was fit by a model in which you have a well-defined disk being transited by a well-defined disk. And we could show that there was no spectral changes. No changes occurred during the ingress to transit or the egress. And on both sides, there was a background or baseline that was well defined, and the same spectrum on both sides. So that kind of ruled out the idea of it being gas and dust, unless it was something that, would itself have constituted an interesting discovery of gas and dust.
So was this discovery made using, did humans have to eyeball all the transit curves, or did you have a machine learning or an AI involved in this?
Well, that's a very interesting question, because in 2018, I had some students visiting, and I and one of my colleagues were working with them and we did everything. We looked at them. Of course, there were over 2,000 of them. There were at 2,600. So we didn't just say, let's sit down and look at all of them. We designed codes, we ran codes, we looked at the events that were picked out by the codes. And over this process, we eventually did look at everything, and we looked at them all in several different ways. And when we picked out this particular dip, there was an interesting story about it, but I will say afterwards, we developed a set of criteria that I think is very simple. You just have to have 1 0 in counts over about a kilosecond and go back to some baseline on both sides. That very simple criteria picks out this one event uniquely.
And so one last question, what's next on this? Is there another
Oh, well, we hope so. We're continuing to look, right? We only analyzed a very small fraction of all of the archived data in other galaxies. So we are continuing to look. We assume that some of our colleagues are now looking, and some of them may even find that in data they've already analyzed, there's some interesting signals. And then, of course, in addition to looking in other galaxies, we should extend the search to our own Milky Way and the local group of galaxies. You might think that's simpler, but it has the inbuilt difficulty that, we don't have lots of, each one has to be studied separately, because unlike being in other galaxies where there are many of them together, so you essentially have a built-in group of data to study. Here you really have to go to each one individually, and there's only a small chance that you'll find something in one individually. So I think this is a problem that will have to be addressed. But it should be very interesting, because we'll learn more from the local ones.
Well, this is an exciting discovery, and one that I am definitely going to continue to follow, and hopefully we'll have you back soon with more news. So thank you again for joining us. This is an honor and a privilege to have you here.
It was my pleasure. Thank you very much for inviting me.
Thank you.
This has been The Daily Space.
You can find more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to the generous donations of people like you. We really need your help to make our budget for this next year. So if you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.